We have just mentioned on the permutation group contains different kinds of concepts. Now let us give a quick review. For example, corresponding to a limited group, we use G to represent. Then the elements in G, it can be written as AI. I'm making a simple example. It is what we have just seen. Corresponding to the internal four permutations, the first permutation is identity element E, which is 1, 2, 3, 4. All four elements remained unchanged. Another permutation is the exchange between 1, 2, 3, and 4 remained unchanged. Another permutation where 1, 2 remained unchanged, 3, 4 exchanged. The last permutation is the exchange between 1, 2, 3, and 4 exchanged. This is a permutation group. Let's analyze unrelated concept. First, corresponding to each permutation, it can use cycles to represent. How many elements are there? To record the structure, we will notice as a conjugacy class form. Then, we will use CKAI to represent how many K-order cycles. For example, over here, the corresponding first identity, there are 1, 2, 3, 4. In total, there are 4 one-order cycles. Then we wrote it as a one-order cycles contains 4. Corresponding to another, let's take a look at this last permutation. 1, 2 exchange, 3, 2, 4 exchange. And this time, two-order cycle contains 2, which is C2A4 is equal to 2, which means it can be written as a two-order cycle. There are 2. But then there's another concept, which is a very new concept, which is known as a K-stabilizer. Correspondingly, what does it mean? Corresponding to these several permutations, its effect is over the first element. They make the first element to be itself. Standardized all these permutations together. It is known as a Z1, which is Z1 is equal to. Over here, identity element will definitely make 1 remain unchanged. Additionally, 3, 4 is changed, 1, 2 remained. This permutation had fixed 1. Therefore, Z1 is equal to E, 3, 4. There's still an equivalent class. Equivalent class means that for such an element, its equivalent class means if it could be transformed into another element, then these two elements belong to an equivalent class. And this time, we will realize 1 can be transformed into 2. Therefore, 1 and 2 belong to the same equivalent class. E1 is equal to E2 is equal to 1, 2. Therefore, the corresponding 3 can be changed to 4. Therefore, E3 is equal to E4 is equal to 3C. And through the analysis of the previous session, we have such a guess corresponding to the number of equivalent classes multiplied by the number of stabilizer might equal to the number of permutations. Just now, over to color the 4 vertex of the square and analyze the permutations may exist this kind of phenomena. To show the relation between orbit and stabilizer, it is just called orbit stabilizer theorem. Below here, we are giving us a complete proof. In the following, we are going to prove the theorem. Assume G is a permutation group of 1 until n. Then EK represents 1 until n under the group G, contains equivalence class of K. Zk is a stabilizer of K. Then we will have this kind of guess, that the number of EK multiplied by the number of Zk equals to the number of permutations. First, we are providing that how many elements do we assume EK have? Assume inside EK there is L element. Then, since it is the equivalence class of K elements, then we can set the first element in EK is K. The other elements are respectively A2 and A3 until A1. Then, at this time, we will realize why they belong to the same equivalence class. Because K element K, which is A1, could be transformed into any following elements. Therefore, K as A1 under PI effect, it can be transformed into AI. After having this kind of thoughts, let's prove to see whether it is true that the number of EK times the number of ZK is equal to G. First, we need to induce all the PI out. From a set of big P, amongst it has include P1, P2 until PL. Then we will have several subsets of permutations. Gi, which is corresponding to subsets of the original permutations. It represents the stabilizer of K times corresponding Pi, and this time we will realize since Zk is making K unchanged, where Pi is referring to transform A1 into AI. then corresponding to elements k under the effect of zkpi will be transformed into ai. A simplified means that gi should be the subset of the composition of g, the corresponding to different I. For example, I and G are different, then its corresponding permutation operation by right should be different too. Therefore, GI intersected with GJ should be an empty set. And this time we will realize since they belong to G, then G1 added up is G2 until G1, GL. It may still be the subset of G, whereas on the other side, we will realize NP should belong to G, this permutation class. Well, K, which is A1, passed through Pj operations, is transformed into Aj. Similarly, it can pass through the inverse of Pj back to K. It simply means K passed through Pj multiplied by the inverse of Pj, and it will be back to K. It means Pi and the inverse of Pj should belong to K stabilizer. Then multiply Pj on both sides. We will realize the left side will be transformed into an operation Pj. Over this side, it will become Zk times Pj. Therefore, the left side, this kind of permutation, it should belong to Zk Pj. We have just assumed that it should be equal to Jj. Then, P corresponding to all the permutations, whereas this side is corresponding to the corresponding subset, and this time we will realize G is corresponding to the left side, whereas this side of J from 1 until L. Therefore, G should belong to J1 plus J2 until JL. From these two equations, we will realize that after these two equations are considered together, then G is equal to G1 plus G2 until GL. We will realize the number of G is split into the number of G1 plus the number of G2 added up until G1. Whereas G1 is following the definition over here, it should be equal to Zk multiplied by P1. Correspondingly to the G2 behind should be equal to Zk multiplied by P2. Continue adding up until Zk multiplied by P L, whereas the corresponding each term, we know that its number should contain L number of different values, whereas the number of each item should be equaled. Therefore, its number should be equal to number of Zk multiplied by the number of L, which is over here. How many equivalence class are there? Then the number of L is equal to the number of Ek. Therefore, the number G is equal to the number of Zk multiplied by the number of Ek. We have then proved the corresponding orbit theorem. With this theorem, we can take a look over a simple example. For what we have been seeing just now, corresponding to a permutation, it has E 1 2 3 4 1 2 3 4, and this time its number of fixed class, which is corresponding to A1, is corresponding one order cycle. It has 4 in total. Corresponding to 2 order cycle permutation, in total there is 1. And this time we will think of to find out the corresponding 1 order cycles, the sum of its number K stabilizers. Is there any connection between them? We will look one by one. Corresponding to A3 is 1 order cycle. There are 2. Corresponding to 4, there is 0 of 1 order cycle. We will realize that, and this time, that within this example, E1 is equal to E2, which contains 1 and 2 elements. 3 and 4, their equivalent class is the same, which is 3 and 4, this kind of set. Then let's design a new table. In this table, each row is corresponding to a permutation, and the corresponding column is for each element. In the middle of the table, pick such a formula. We use SJK to represent J row K column. Its operation may pass through. If corresponding to this element, under this permutation it does not contain any change, then we will write it as 1. If its element contains changes during the permutation, we will write it as 0. Continue with the same way down, then we can list out such a table. Then we will realize if we count row by row, it is just corresponding to such a permutation. How many elements are remained unchanged, which is 1 order cycles. How many are there? Correspondingly, it is C1Aj. If we looked vertically, then we will realize if we solve it vertically, it is equivalent to how many permutations does element have. for it is to remain unchanged, which is the concept of a k-stabilizer. Then if we add up with the horizontal ones, then finally produce the result added up with the vertical ones, the final result and their result should be the same. And this time we will realize that the column for this corresponding row, it should be C1aj for the sum of the k column. It is z getting zk, whereas the summation of all elements is equivalent to either zk from 1 until n to perform accumulating summation or corresponding to different permutation of C1aj, j from 1 until g. Then for now, their number is equal. After having this kind of concept, we will realize, well, we are looking for equivalence class. Maybe we do not need to find the k-stabilizer. We can just use directly how many such one-order cycles do we have to perform a direct calculation. Then over here, we can use ek multiplied by zk is equal to g, this particular concept. Similarly, just now we have just picked a special example to have a look. Under general case, we can correspondingly perform permutation on A1 until AG to see if there are any elements contain changes. Similarly, we will get the concept of a sum value corresponding to the sum number of k-stabilizers. The accumulative summation equals to the sum value of the number of one-order cycles of whole permutations. After having this kind of concept, let's calculate how to find the equivalent class. Assume 1 until n, this many elements is split into L equivalence class. Then 1 until n can be written as ZA1 plus ZA2, continually adding up until ZAL. And this time we have two equations. One is that we have mentioned the orbit theorem, which is the number of EK multiplied by the number of ZK is equal to the number of whole permutations. Another one is through the design of table. We know that all the number of k-stabilizers accumulative summation of k from 1 until n equals to the summation of one order cycle in all permutations. Well, after having this concept, let's take a look. For example, I and G belong to the same equivalent class. They are on the same track. Because EI's is equal to EJ's, the number of EI then naturally equals to the number of EJ. Whereas at this time again we know that EI multiplied by the number of ZI should be equal to the number of permutations. Therefore corresponding to then, because inside the equivalence class the number is the same, then the corresponding number of stabilizers must be the same too. Therefore the number of ZI is equal to the number of ZJ. Then because in each equivalence class we know the cumulative summation of ZI should be equal to the corresponding number of equivalent class multiplied by the corresponding k-stabilizer number inside. Whereas for this number we have total of L equivalence class. For all the mentioned ones, characterize ZK based on the equivalent class. It's equivalent to corresponding from J from 1 to until L. Whereas each I belongs to one of the equivalent class. To find the summation of its ZI number, each over here is equal to, therefore their number is equal to EAI, AI multiplied by ZAJ. From this equation we can see that it is exactly same like what we have said in orbit theory. The sum of product of the summation is equal to a constant, where is the number of permutation. Then over here it should be equal to the number of permutations, whereas accumulative is J from 1 until L, then it is equivalent to the total of 1 L elements of constants performing addition. Then naturally we will manage to find L is equal to how many the L multiplied by the number of G is equal to the sigma of K from 1 until n, the number of k-stabilizers. Then the number of 1 L naturally is equal to all the number of k-stabilizers divided by our known number of permutations. Of course, we also know that k-stabilizer is not easy to find, but the number of k-stabilizer is a cumulative summation equal to all the number of one-order cycles. Then it's naturally equal to what we have seen after having a permutation. Then to find out all the permutation corresponding to the number of L one-order cycle, then divided by its corresponding all the permutation, the answer is the number of equivalent class.